Hey class, welcome back. Today we're taking a look on pages S11 to S14. Well, we'll see how far we get. On Unit S, Simple Linear Regression, starting on page 159 of your manual. In the last couple of lessons, we talked about how to calculate the slope and the intercept for the sample regression line. And what I said there was that you can't really take a look at the magnitude of the number and decide whether it's significantly different from 0 or not. Remember, a slope of 0 means that the x variable has no effect on y. And that's because it has to do with the magnitude of the numbers, the x in terms of the y's and so on. And I went through an example where you can actually have a very, very low, almost 0 looking slope, but because of the units, then it's actually still significant. So we're going to come up with a formal t-test on testing whether the slope is equal to 0 or not. Now, once again, why is it important that we're talking about the slope being equal to 0? Well, let's take a look here. Okay, so let's take a look at a real simple graph right here. And you're going to have here an x and a y. And if we ended up with a sample regression line that looked like this, so it's just a horizontal line like that, then what that's saying is that if x increases or decreases, it has no effect on y. So the slope is equal to 0, and of course the correlation, the r, would be equal to 0. So we would have the b1 equal to 0, and of course the r, the correlation coefficient, equal to 0, meaning that there is no linear relationship between the two. So when we're doing a test on a slope, we're usually looking at whether the slope is equal to 0 or not. Now down here, we've got, just as the generic form of the test, is that we're testing whether the beta 1, remember we're never testing B1, that's a sample statistic, we're talking about the population parameter here, in this case the slope, that beta 1 is equal to some number k. Now it could be that k is equal to 0.5 and we're asking, hey, has the slope changed from what it was last year when it was a slope of 0.5? So we could look at a question like that. But really, we're generally interested in, and this is all we'll look at in this particular course, is whether the slope is equal to 0. Why? Again, because the slope of 0 means that x variable has no significant impact on the y. And so really we shouldn't include it in a regression model. So we'll be looking at the test HO that beta 1 is equal to 0 against the alternative that it could be less than 0, greater than 0, or not equal to 0, like that. All right, let's take a look at how we do that then. Oops. So the test statistic then, remember step number 1 of a hypothesis test is always your HO and your HA. Step number 2 is the test statistic, and it's just a simple T-star formula. So you've seen this before in this form. T-star is equal to x bar minus some hypothesized mu divided by S divided by the square root of n. And this is just the standard error of the x's. Okay, so it's the not the standard deviation of the x's, but the standard error. So in our particular case then, what we've got is that this guy here is the standard error, and it's calculated this way. So it's based on the overall regression error, the error of the residuals or the errors, and plus a term here which makes it the standard error of the slope. So it's got the same form as a usual t here, like that, and this should be the s of the x bars. There we go, that looks better. but it's dealing with the sample statistic, the hypothesized value, which is just going to turn out to be 0 in our null hypothesis, and then the standard error of the slope. The rejection region is, this is based on n minus p minus 1 degrees of freedom. It's a t-test. It could be upper tail, lower tail, or split, depending on the form of your alternative hypothesis. And the p is equal to, remember, the number of explanatory variables. So in a simple linear regression model, would be equal to 1. And then step number 4, we calculate the T-star value, and then we come up with our conclusions. So just like we always do. Let's take a look at this. Oh, before we go into that, you can also do a test on the intercept. And the intercept looks really similar. The SB0 value looks very similar to the SB1, except that there's an additional term here in the numerator. Otherwise, everything else is the same here. All right, let's take a look at a couple of examples here. This is on page S13. So test the two hypotheses that the intercept is equal to 0 and the slope is equal to 0 for the age push-ups example. And so I'm going to, let me find the right page here. I'm actually going to do this in, it's a large page here. I'm going to split this in half. So on the top here, I'm going to do the test here for the slope. So let's take a look then at the slope. And we're going to be testing then that the slope is equal, whoops, the slope is beta 1 is equal to 0 against the alternative. Now this was the age push-ups example, and so when we looked at this earlier, I'm going to test this as a two-sided test because I don't know whether there's a positive relationship or a negative relationship. I would expect that there would be a negative relationship. Of course, I know that we've already calculated the coefficients already in a previous lesson, but let's pretend that we haven't. So if I was just starting this over again, this is what I would do, is that they're not equal to 0. So that's step number 1. Step number 2 is that the formula that we'll use is T star is equal to the B1 over the SB1 value. Okay. All right, let's take a look then at what that looks like. Step number 3. Actually, I'll do step number 3 over here, just because of room here. This is our decision rule. So let's take a look at where our critical region is, like so. So here's a T distribution. N in that case was equal to 12, so this is going to be 10. So that's 12 minus 1 minus 1. 1 for the x, 1 for the y. So 10 degrees of freedom. And because this is a two-sided test, and what we're going to do is we're going to have the alpha split in half, so we'll have 0.025 here and 0.025 here. Like that. And that value turns out to be, that critical value is plus and minus 2.228. All right, now let's go and take the sample. We get the sample statistics. We stick it into the formula. And first we need to calculate the SB1 value. So the SB1 value is equal to the SE times the square root of 1 over the sum of the x squares minus the sum of the x's squared over n. And I'm using, let's see, back on page S6 and also S10. So that's where we get all the necessary values that we need here. So the SE value then turned out to be 7.17 times 1 over 25,921 minus 503 squared over 12. And that is 0.103. Okay? Now, the T star is equal to minus 0.265. Remember, that was our slope that we'd calculated back on page S6 here, divided by 0.103, and that turns out to be something or other, minus 2.57. Minus 2.57 is right in here. And so what we would do is we would reject HO, and that means that we would say that the slope is significant. It's significantly different from 0. So slope is significantly different from 0. In this case, negative. And therefore, that age is a significant determinant on the number of push-ups that a person can do. Push-ups. Okay. All right. So that's how you do the formal test here then for the slope. Now let's take a look at the intercept. So I'm just going to put a line across here. There's my tools. Okay. All right. So let's take a look now at the intercept. And in this case then, we're going to test here that the slope is equal to, the intercept is equal to 0 against the alternative that the intercept is not equal to 0. Now, by the way, you'd look at this and you say, well, obviously it has to be positive because the slope is significantly negative, and so you've got to have a positive intercept. And usually we're interested in testing the slope. Sometimes we're interested in testing the intercept, though, and especially if we're asking the question, has it changed from what it was before? So that 0 could be some other number, some k. Last year it was 40. Has there been a significant change, an increase, a decrease, or just a change? So you could do that, but we will test it against 0. Same format of the formula, except that we're talking about B naught over S B naught. And then we would have, your critical region would be exactly the same as above there. So we've got a T with 10 degrees of freedom. We've got a critical region here. Of minus 2.228 and plus 2.228. And now let's go and do the calculation. So again, we're using the values from page S6 and S10. And so we've got the SB naught value is equal to SE times the square root of, and the numerator looks a little different here. It's not 1 like it was for the slope, it's this. And then the denominator is the same. Okay, so let's see that. So we're going to have SE, which is 7.17, times the square root of, let's see, 25,921 divided by 12, and then 25,921 minus 503 squared over 12. And that comes to 4.793. All right, T star is equal to 32.862, which we got from page S6, and then divided by 4.793, and that gives you a really high T star value, so it's very significantly positive. So we would reject HO and conclude, therefore, that the intercept is significantly positive, which there's no real surprise with that. Okay. Now, at this point, then, you might want to stop and just try the next problem here. I'm going to just continue on here as if you have done that. So, of course, you can stop this at any time and practice. So let's do the same then for the house price example. And so I'm going to start here then with the slope. And we're taking a look at page S7 and S11 in this particular case then. So that's where we did that from a previous, no, S10. S7 and S10, yeah. And we talked about that in the last lesson. All right, slope. Step number 1, that beta 1 is equal to 0. In this particular case here then, suppose your decision maker, I want to do a one-sided test here, suppose the decision maker here then says that you figure if there's a relationship, they would expect it to be positive. Now again, that's something that the decision maker would tell you, and the default is always that there is it's a two-sided test. But if the decision maker says, well, I think if there's a relationship, we would expect it to be positive, and of course we can use some common sense on that in terms of house sizes and house prices, then that's what we want to test here. Again, on a say a test question, I would be more specific in terms of that. Number 2, so T star is equal to B1 over SB1. Step number 3, critical region and the decision rule. So in this case then, we would have T still 10 degrees of freedom, but what we would have then is the whole alpha, critical region, is going to be equal to 0.05. It's going to be an upper tail test, and that's based on the sine of HA. So if you look that value up, you're going to get, what is it? 1.943. And that is wrong degrees of freedom. That's actually 6. So that's 8 minus 1 minus 1. That's better. So 6 degrees of freedom. And 1.943 is your critical value. All right, let's do a calculation here then. So step number 4, we're going to calculate first the SB1 value, and that's going to be equal to the SE times 1 over sum of the x squares minus square of sum of x over n, and that will be, let's see, for this problem it was 39.19, and this is from page S10 that we're getting that, times the square root of 1 over 3855 minus 165 squared over 8. And that comes to 1.844. Okay. T star is equal to 4.641, and that was from page S7, over 1.844, And that comes to 2.52. Now 2.52 is clearly in the rejection region. It's in the critical region. And so therefore we would reject HO and conclude therefore a significant positive relationship. So that means then that as the size of the house increases, so does the selling price of the house. Okay, let's do that now again for the intercept. Now in this particular case, you might say, well, wouldn't the intercept be positive as well? And the answer is not necessarily. Let me draw a little picture over here on the side. So remember, the thing about regression, we've got an X and a Y here. And regression is good within a certain range. So it's certainly possible that you can have a negative intercept, but within the appropriate range of the X's, it's still positive. Okay, so it is possible that you can have a negative intercept here. For that reason, we test the relationship here then for the intercept, that it's a two-sided test. Now again, we generally don't even test the intercept. That was a terrible line. But you might have some problem where you're asked to test the intercept, or again, it could be that it's tested against some other value, some K of what it was last year, and see if there's been a change or something. We'll just test that it's equal to 0. T star is equal to B naught over S B naught. Step number 3 is this is a T distribution with 6 degrees of freedom, 8 minus 1 minus 1. And we'll take the alpha and split it in half. So we'll put 2.5% in each tail. And what is that critical value? 2.447, it looks like. And I assume you know how to look that up on a T-table. There we go. All right. SB naught is equal to SE times the square root of the sum of the x squares over n over sum of the x squares minus square the sum of the x's over n. So that's 39.19 times the square root of 3855 over 12 divided by 3855 minus 165 squared over, not 12, 8 over 8. This should be an 8 up here. And so then that comes to, let's see, what do we get here? 40.47. And so finally then we would say T star is equal to 71.02 over 40.47. Remember, we calculated the 71.02 back on page S7. And that comes to 1.76. And so therefore, do not reject HO. So this intercept is not significantly different from 0. Again, it's probably not all that interesting. Let me move that up there. Here we go. But that's how you do the test. And that's where I'm going to stop it for this lesson. Thanks for listening.